Hey guys, I'm going to go over the notes for the second part of chapter 3. Here we're going to talk about the solutions. We talked about this a little bit in chapter 1, but a solution is a homogeneous mixture. It means it only has one phase, and it's uniform without. And so an example of a heterogeneous mixture would be milk. It seems like it has one phase, but anything that's thick in substance like this, if you look at it microscopically, you can see different parts to it. Whereas something like salt water, if you dissolve salt in water, the ions are completely surrounded by water molecules. And it's uniform throughout the solution. And so it's one phase, it's uniform, and any part that you take of it would have the same concentration. A solution is made up of a solvent and a solute. The solvent is the dissolving medium in the solution, so that's what the solute is being dissolved in. The solute is the substance dissolved. So, for example, in the saltwater solution, the salt would be the solute, the solvent would be water. The solvent is usually the one that's present in the greatest amount. The most common solvent is water. This is almost always what things are dissolved in. And then solutes can be anything that's dissolved in the solvent. The solute is soluble in the solvent, meaning that it's capable of being dissolved by it. So there are certain things that aren't soluble, like if you put sand in water, it wouldn't dissolve, it would be insoluble. But here we're going to be dealing with solutions that have a soluble solute. Here are some different types of solutions: gas and gas, gas and liquid. Most often we are going to be dealing with solids and liquids. Sometimes we'll be dealing with liquids and liquids. But these are other different kinds of solutions. The concentration of a solution is the measure of the amount of solute in a given amount of solute or solution, or solvent or solution. And so in chemistry, the one we use the most is called molarity, because it refers to the number of moles in a liter of solution. So if you're going to a drugstore and you're getting some sort of substance like hydrogen peroxide or rubbing alcohol, then they're probably going to give you the concentration in weight percent or volume percent. But in chemistry, we're going to deal with molarity because it's going to tell us the number of moles. And this is the most important thing for us when we're dealing with chemistry. So molarity is equal to the moles of solute over the liters of solution. So solution is the solute and the solvent together. So for molarity, how would you prepare a 0.1 molar solution of sodium chloride? And so we use these things called volumetric flasks because they're really accurate in measuring amounts of the solvent. And so you first put 0.1 moles of sodium chloride, and you measure that, and you put that into the flask. You want to put that in first because if you put it in after, then it could increase the volume. So you want to put it in that, and then add water to equal a total volume of 1 liter. So first you're adding the solute, you can add some solvent to dissolve it, and then pour until you get to the line, which would tell you that you got to 1 liter. So now for calculations. It says you have 3.50 liters of a solution that contains 90 grams of sodium chloride. What is the molarity of that solution? So the first thing I'm going to want to do here is I'm giving grams. I want to convert that to moles. In the lab, usually what we would weigh out is grams, and so we're often going to be calculating grams for moles. It's rare that if you were given something in the lab, you would know how many moles you have. Usually you'd weigh it on a scale, find out how many grams, convert that to moles to figure out the molarity. So we want to know how many moles of sodium chloride, and we're given 90.0 grams of sodium chloride. So conversion factor with grams of sodium chloride on the bottom, moles of sodium chloride at the top. Here, from the periodic table, I'd find that it's 22.99 for sodium, 35.45 for chlorine, and so that gives me 58.44. So I'm going to put that in here, 58.44 grams per mole. Divide 90 divided by 58.44. Get 1.54 moles of sodium chloride. So then I'm going to take this and divide by liters of solution. So the molarity then will be equal to 1.54 moles divided by 3.50 liters of solution. When I divide that, 0.44 is what I get. So I get exactly 0.44. However, we need 3 significant figures. So this is an example of when you're going to be adding an extra significant figure. So I'm going to add a 0. And so that's 0.440 molar NaCl. Here, it says you have 0.8 liters of a 0.5 molar HCl solution. How many moles of HCl does this solution contain? And so there are 2 ways you can do this problem, and I'll do it 2 ways for you. The first one is just to look at it as an algebra equation where you have molarity is equal to the moles over the volume. And so because we're given the molarity and we are looking for moles, we're given the volume, and so we're just going to plug in that equation. And so it would be that 0.5 moles over liters of HCl is equal to the moles of HCl over the volume, which is 0.8 liters. Multiply each side by 0.8. That cancels, and so you get that the moles of HCl is equal to 0.4 moles of HCl. So you can do it like that, and that's fine. As long as you're showing your units, that's fine. For me, it's a little easier for me to do this, making the molarity into a conversion factor. And so the way I would write this is that I have 0.5 moles of HCl for every 1 liter of solution. And so then what I'm going to do is say that I'm looking for how many moles of HCl, and then I'm given 0.8 liters, and then I just want to use molarity as a conversion factor. For every 1 liter, I've got 0.5 moles. Liters cancel. You get 0.4 moles of HCl. So whichever way confuses you, do the other way. Either one. It's kind of good to think about the fact that molarity is a conversion factor, though, because then you can do more complex problems using it as that conversion factor. But either way, you're multiplying the 2 things, your units are canceling, you're ending up with this answer. Dilution is the process whereby the concentration of a solution is lessened by the addition of solvent. And so if in the lab you have some stock solutions that are more concentrated and you need a certain molarity of a solution, you can dilute it in order to get a different molarity solution. This formula is what we can use for dilution. And so here your book has liters there, but we can put that as V1 and V2, either one. And the volume can also be in liters or it can be in milliliters, as long as it's consistent. Basically, it just needs to cancel out here. And so usually for these equations, you'll be given it in milliliters or liters. As long as it's consistent, you can use this equation. And so here, an experiment in a general chemistry laboratory calls for a 2.00 molar solution of HCl. How many milliliters of 11.9 molar HCl? So how many milliliters of this would be required to make 250 milliliters of 2 molar HCl? And so this is what we're making, and so this is going to be our volume 2. And we're making something of this molar, so that would be M2. How many milliliters? That would be our volume 1. And here, this would be M1. And so the equation is going to be M1 V1 equals M2 V2. So we've got 11.9 molar times our V1 is equal to 2.00 molar times our V2, which is 250 milliliters. So we're going to multiply, or we're first going to divide by this, 11.9 molar. So that cancels, the molarities cancel out. V1 ends up being 42.0168, which we end up having only 2 significant figures because that's not significant right there. And so our significant figures are going to be 42 milliliters, like that. Here, what is the final concentration of a solution produced when 225.5 milliliters of this molar solution is allowed to evaporate until the solution volume is reduced to 45 mils. So this is actually making it more concentrated, but we can still use the same equation. And so the volume is reduced. This is the final volume. Final concentration is what we're looking for. Here is M1 and here is V1. So we have 225.5 milliliters times 0.09988 molar equals M2 times 45.00 milliliters, divide. So milliliters cancel. When you multiply that out, your calculator should give you 0.500509.8. And I want 4 significant figures. So we get 0.5005 molar. And that would be the final concentration. And so it started out at that concentration, it became more concentrated at the end. Okay, here are some other units of concentration. Percent composition is what's used to label most household chemicals. And so percent by mass would be 15% by mass of sodium chloride solution, the mass of the solute over the mass of solution times 100. by volume would be volume of the solute, volume of the solution times 100. For example, find the percent by mass if 25.0 grams of potassium hydroxide are dissolved in 500 milliliters of water. Here we're going to assume the density of water is 1 gram per milliliter, and so that allows us to see that that would be the same as 500 grams of water. And so here our equation is going to be the mass of we want the mass of the solute over the mass of the solution. And I'm going to usually abbreviate solution SOLN. So that's going to be 25.0 grams of KOH. And that's going to be this times 100. And then on the bottom, I'm going to put the solute plus the solution, 500 grams of H2O, because it's a total solution, not just the solvent. So you want to add those together. So you get 25.0 grams KOH over 525.0 grams of the solution times 100. You should get 4.76% KOH. And that is percent by mass. Percent by volume is going to be the same. Solute plus the solution. And so you just want to be careful that that's not the solution, that is just the solvent. And so what we want here is we've got 10.0 milliliters of ethanol. I usually abbreviate ethanol ETOH over 10.0 milliliters ETOH plus 500.0 milliliters of water times 100. 10.0 milliliters of ethanol over 510.0 milliliters of solution times 100. And so multiply that, or divide that, multiply by 100, and we get 1.96% ethanol solution by volume. Okay, last slide just tells you what parts per million is. And so basically this is just like, what was it? Percent by mass, except for percent by mass, you multiply by 100. Parts per million is when you have something that is really, really small amount. These are like impurities or things that could hurt us in water. And there's limits to how much that can be in. So the EPA standards here in America for these certain things, so it's different around the world, but here the ozone has to be 0.075 ppm, lead 0.015 ppm, chlorine 4 ppm. And so because it's such a small amount, instead of multiplying by 100, you multiply by 1,000,000, and that gives you a number that's more easy to deal with. And so 4 ppm is actually a really, really small number, but it's easier to refer to it in terms of the parts per million because we've multiplied by 1,000,000. And so we're not going to do any problems with this. This is just for you to know, and I might ask you one quiz question about what this is and what it means. Okay, so this is everything for this chapter. The rest of this chapter. So this is an easier chapter. This is probably going to be a good time for you guys to get caught up on any other things that you need to do. Please let me know if you have any questions. Go over the worksheet and practice problems and look at the answers, and contact me if you have any questions.